going to talk about some work today with my student Alex Damien, Maddie, whom you've all heard from 2 days ago, and Chile, whom you've also heard from. Maddie's at USC, of course, and Chile was a former postdoc, now at NYU Courant Institute. So today I'll talk about learning representations or features using algorithmically with gradient descent. As a very fast motivation, pre-trained models are all the rage now. A very standard paradigm is you train on some large data set that's not exactly from the same distribution as the data you will test on. You extract some features or a representation from this large pre-trained model, and then you fine-tune or adapt on a small validation set and then use that as the final predictor. So this can be supervised or unsupervised. The pre-training stage both work very well. This figure is taken from this report by the Stanford group. And this is a pretty standard pipeline these days. And my goal of this talk is to understand some simple cases where we can provably learn good features and representations. So the questions I want to look at are what kind of pre-training tasks do we need, what kind of architectures, and how many samples you need to do this. Okay, so essentially the observation in the literature right now is that neural nets can learn representations of the data which allow for efficient transfer learning or in generalization. Roughly speaking, the weights have like magic information in them. They were trained on task A and they can work for task B. So the weights are not only just good for predicting the task that they were trained for, but somehow they learn features and representations that are useful for other tasks that can be quite different. All right. Starting from roughly 2018 or 17, a lot of the work on deep learning theory has focused on a regime in which it's equivalent to kernel methods. This theory is very useful for optimization if your only goal is to show that the training error decreases to 0 or decreases to an approximate global minimizer. This theory is extremely useful. It's essentially the only generic tool we have even today for proving theorems of that style. Maddie briefly mentioned this. However, this theory cannot explain or even address transfer learning at all because the features never changed. In this, if you forced your algorithm to be equivalent to the kernels, the weights are essentially, the representation layer would be frozen and you can never get any benefit from transfer. You would just have to retrain from scratch. Okay. So for the first part of my talk, I'll look at supervised representation learning, and I'll give an end-to-end analysis using gradient descent. Then if I have time, I'll talk about self-supervised learning briefly. Okay. So here's an interesting toy example. For the first part of this talk, the major assumption will be the covariates. The distribution of the input is Gaussian. So you can tell I'm a theorist. And the signal follows y equal f star of x. Okay, f star will be the ground truth. In this toy example, it'll depend on this fourth order polynomial and only on a single direction. So this function, although the ambient dimension can be very high, it only depends on a single relevant direction, and it's a degree 4 polynomial in that direction. Okay. So this function you can think is pretty simple. If I told you the direction u star, you just fit a univariate polynomials that needs samples, something like order of the degree, and you would be done. Okay. Let's see what happens when we run two standard algorithms. One is the blue line is I train a 2-layer neural net with, it's very standard ReLUs, and I used a initialization scheme that's kind of small, the mean field or mu p initialization, they're equivalent. And you can see that the test loss can drop below this line. I'll tell you in a second what is this dotted line. Okay. And this red line, random features or kernel method, it just levels off and gets stuck at this line. So what's happening here? Essentially what's happening here is that the kernel method, the sample size or the width was constrained to be roughly d squared. So it can only learn as well as a degree 2 polynomial. So the relevant quantity here is to look at log base d of the width or sample size, the smaller, the worse of the two. And that's at best how well a kernel method can do. So here, this line at around 0.7, okay, this thing stopped working anyway. Around 0.7, that's the best you can do with a degree 2 polynomial. So you see that g of x is degree 4. I'm in Gaussian space, so the best you can do is keep the second order Hermite expansion of g, meaning you take the dot product with the second Hermite, x squared minus 1, and keep that. And that's exactly going to give you that line slightly under 0.7. And that's exactly what the kernel method converges to. The neural net, when you start passing number of samples, starts passing d squared, you can see there's a phase transition around 2, between 2 and 3, and it starts improving. Eventually, in the beginning, it also cannot do anything. There's just not enough samples. And eventually, it can start passing it, and it can learn to high accuracy. And at the end, you can see that there's some feature learning happening. The neural net one, all of its neurons are in the direction of U star. Okay. Yeah, so here's an animation of what's happening. Sorry. Yeah, so we're going to play it a few times. So what happens is that here, the dotted black line is the best degree 2 thing. And that's exactly what kernel methods will fit, and they stay there forever. So you can see on the right-hand side, you just go, you fit to that, and you stay stuck there. In the full network with gradient descent, with a kind of small initialization, mean field or mu p, you go to that one, and then you snap out of it, and you eventually will learn the degree 4 thing. And that's also reflected in the loss here. The neural net plateaus here for a brief amount of time, and then it can escape it. So our goal is kind of to get something like this, where there's feature learning happening, and you actually learn the U direction. Okay. Oops. Okay, yeah. So, oops, sorry. I apologize for the question marks. The citation should be to a series of lower bound papers. Some of them are by Andrea Montanari, some are by myself and Tengyu Ma and others. Essentially, this group of theorems say that, that when you have a rotationally invariant kernel and your number of samples is dimension to the p, you can only learn polynomials of degree p and no better. So if you look at the kernel, either the random feature kernel, the NTK, it doesn't matter which, of a two-layer net or even any fully connected net of any depth, you need both number of random features bigger than d to the p and sample size bigger than d to the p. And what happened here is one of them was capped, so where at p equals 2, so you can only learn as well as degree 2. And d to the p is a bad result here in the sense that for that previous signal class, you should only need d samples. If you just by parameter counting, the minimax rate for this function class is d. Okay. Okay, so that's exactly what's happening here. Our goal is to show that gradient descent can learn something close to the minimax optimal rate, but in a regime where kernel methods kind of fail. All right. So if I have a polynomial of this type, x1 to the p, and a general polynomial of degree p with arbitrary coefficients, the kernel method, the the rotation invariant kernels all need samples and width d to the p. And the question is, can you do better by training a neural net? It's very clear that if I knew my function was like axis aligned like this, then you can get better sample complexity, at least statistically. This is very simple. The main question is how to do this algorithmically. So of course, for arbitrary polynomials, if I want to be able to learn all polynomials of degree p in dimension d, that's impossible. There's just d to the p of them. That's just how many there are, and you can't do better than this. Okay. But for structured polynomials, this is possible. So for the rest of the talk, I'll focus on a special case of structured polynomials, which I think is fairly natural. So I'm going to look at polynomials f star. They're of degree p. There's some normalization here. The output is roughly 1. And there's this hidden subspace s star of dimension r. And the function is of the form g of u star x. So g is general. It's anything of degree p, and it's a polynomial, or it can be more general. It can be anything in a certain RKHS. But for now, let's say it's polynomial, and you have this projector matrix that reduces from dimension d to r. So in the example I showed you, r was 1. There was only one relevant direction. Here, you should think of r as much smaller than d. Maybe there's only a handful of directions that matter, but in the ambient dimension was very large, 10,000. Okay, so what is our goal? And of course, the assumption is you have Gaussian Gaussian covariates or features, and there's some additive label noise on the y. Okay. The learner or the model will be a standard two-layer network of this form. Sigma is ReLU. Okay. And the primary assumption, besides Gaussian covariates or features, will be about the expected Hessian. So this is an important assumption. It's always true that this Hessian has rank at most r. You can just check, you can just calculate the gradient. This doesn't even need that the features are Gaussian. It's always the case, it's rank r. This is intuitive. The function only varies in the r coordinates, so the gradient and the Hessians can always only vary also in those coordinates. But the important non-degeneracy assumption will be that we assume it has rank exactly r. So a bad case is that its rank deficient. For example, if the function f star of x was the 10th Hermite polynomial on the first coordinate, this matrix would be degenerate. It would be just the zeros matrix. And that would be a bad case. In a smooth analysis setting, if you look at the set of polynomials and you add a small noise to their coefficients, this is actually well conditioned. And that's what this assumption is saying, is that the condition number of this we're going to call kappa, and our bounds will depend on this. The division by square root r is correct here. It's because that's the size of the eigenvalues here. So in a function that's well conditioned, this would be order 1 quantity. The root r is just some scaling here. And we know that there's a simple lower bound here you can prove, is that if you violate the non-degeneracy assumption and you restrict yourself to what are called correlational statistical query algorithms, you need at least d to the p, which is what I said was bad, what the kernel methods get. So at least restricted to correlational statistical queries, in some limited sense, this is necessary. This is learnable in the SQ model, though, without this assumption. If someone can ask me after if they're interested in a reference for that. Okay. We're going to look at an algorithm that's a modification of gradient descent. It's not standard gradient descent. The major change is we delete the linear part. We're going to just fit a linear least squares. We're going to get rid of the intercept and the linear least squares. The simplest form of the algorithm is you do one gradient step on the hidden layer and then many on the A's. This part afterwards is not essential. So the prediction looks like this. There's many variants that kind of work. So this is the algorithm. Do one gradient step, and then many on the A's. There's many variants that also work. All of them require removing the linear component. The linear one causes some annoying issues. You can do several gradient steps on the W, drop the step size, then do many small ones on the W. This is fine. You can do several ones on the W, then many small ones on the A. These are all fine. You can train both. It doesn't really change anything. The point is you need this discontinuity. You need a place in the algorithm where you drop the learning rate from big to small to force, essentially, for the experts, we all know that when you use small learning rate, big initialization, small learning rate, you can mimic kernels. Okay, this is a well-known result. But the goal is I don't want to mimic a kernel at the random initialization. I want to do it after a little bit of feature learning. And that's what exactly the first phase is here, the one or several steps. I'll look at the simplest algorithm for now, but the analysis and the results are essentially unchanged. Okay, so the intuition, like I said, is that we know how to get neural nets to mimic kernels, at least since like the Rahimi-Rect results or Amit Danieli had many results of this type. And more recently, the neural tangent kernel literature. There are several ways to do this. You can do it by training only the A's or training the hidden layer with small learning rates. And the random feature is, of course, just a special case of NTK. So if you told me the subspace, the span of the U star, this problem is almost trivial. I would just initialize the neurons at random in the span of U instead of all of RD, right? The span of U is some R-dimensional subspace of the full RD. I initialize at random in this subspace and run kernel method or train the output layer or train NTK. All of these would work. And then I've solved the problem. So the more interesting part is why do you learn good features? Why do you learn the subspace? And you not only need to learn the subspace, you need to learn things in a subspace that are sufficiently still random in that subspace. Okay, so for now, here's the theorem we proved. The sample size is, for this result right now, is quadratic in D squared times some poly R factors. And then the risk is going to be dr to the p. So the ideal thing would be if you had r to the p. We have an extra d here. And this is sort of the transfer learning. If I have m new samples from a new target function, and I train just the output layer. But let me kind of just describe, let's say n and m are equal for now. Sorry, m is the width here. Sorry, m is actually the width here. I'm confused myself. So essentially, you need number of samples, dr plus r to the p. That's sort of what the minimax rate for this class is. And we're off by a factor of d. So it's the minimax rate times d. That's kind of how I would read this result. And the width is r to the p. And this is necessary for this. You can kind of see, even if you just did random features and I tell you the subspace, you would need r to the p. In comparison, kernel methods need both sample size and width d to the p. Okay. Oh, and this funny way of writing is because this is actually the correct way to look at it because I have noise and the noise was size zeta, so I'm subtracting off the noise here. Okay. There's a similar result for transfer learning. Let's say I have a new target function, f tilde. This f tilde depends on the same r-dimensional subspace, but it's a different function. It depends on the same r coordinates, but it can be an arbitrarily different function. So what we do is we pre-train using the feature learning, throw away the head, keep only the hidden layer, and then retrain the head. That's the algorithm. We retrain the final layer. And you have big N samples. So then your rate is now r to the p over n, and it's independent of the dimension, right? You only depend on r. And r to the p is, again, optimal because you can have an arbitrarily different polynomial on the subspace, and that clearly needs r to the p samples. So the transfer learning only requires samples and width r to the p, independent of the width. The point here is you're completely independent of width. And in the pre-training, the dependence on the width is a fixed polynomial. It's never d to the p. It's like d or d squared. And actually, I'll talk about later how to make it linear in d. Okay. Okay, so let me kind of just sketch kind of the proof. The idea is not too difficult. We're going to look at the kth Hermite tensor of the target function. That's very simple. That's actually just the expectation of the kth order derivative and then integrated over the data. These are also, because the input is Gaussian, this also happens to be the Hermite coefficients of order k. Like I can take any function in Gaussian space and write it as the sums of the Hermite polynomial tensors with coefficients. And the first order coefficient, there's d of them. And then the second one's a matrix, there's d squared of them. The third order is a tensor of order 3, there's d cubed, and so forth. Okay, so we're going to Hermite expand the gradient. And okay, I've written the Hermite expansion here. This is just a calculation. But what's important is that what you're left with is these terms here. Okay. So these terms disappear because remember, these terms turn out not to matter because I do this linear regression pre-processing step. And so I just remove them. This one's a constant independent of the thetas, the parameters, so it doesn't matter. And the important thing is this one here. So what happens is that you need this to extract information from the kth tensor. You need to concentrate the gradient to accuracy roughly d to the minus k over 2. Okay, so we're actually only going to use the second order tensor, the matrix, so it's k equals 2. And that's where you get the d squared samples from. Okay, so this term is very good. Remember, my non-degeneracy assumption was exactly about this T2, which is the Hessian, the expected Hessian. So this guy times the W is sort of like a random feature in the space, because I told you that the H, the span of it is exactly the subspace. So if I do one step of power method on this matrix, I now get something in the span of U. It's not, perfectly isotropic, and that's handled later in the kernel analysis or random feature analysis, but it's close enough to isotropic up to these kappa distortion factors, which was the conditioning of this T2. So this term is what we kind of care about, and where all of the feature learning is happening, is you're just getting things in the span of the H's. Okay, so roughly speaking, if I have d squared samples times some poly r factors, my gradient looks like something like the second order tensor times the W plus some perturbations. Okay. And then that's exactly what this first step is doing. You get HW, one step of power method with respect to a matrix that has the correct span. Okay. They're approximately Gaussian with the wrong covariance. They're not isotropic on the subspace. They're distributed according to covariance, which has condition number kappa squared, because H has condition number kappa, and they're supported all on the span of U star. So they're like up to kappa factors, poly kappa factors, isotropic on the correct feature space. And then afterwards, you just, then it's very standard. Now, I do one gradient step, I construct the A stars, I can just calculate the norm of the A star I constructed, and it happens to have norm something like r to the p, and then this problem is now even convex in the A's now. So if the existence of a solution plus convexity plus gradient descent convergence and convex optimization, just standard convergence analysis after t steps, where t is polynomial and everything, you have the loss small and the norm is not too big. And now it's just standard generalization analysis for kernel methods. Is that this kernel can learn, the kernel induced by ReLUs can learn polynomials of degree p, which I think most of us know already. So then it's just standard Rademacher generalization bound for a two-layer network to bound the risk by the empirical risk, and we've made the empirical risk, we've made the empirical risk very small, and then it's just a standard generalization bound. Okay. So like I said, this result is suboptimal by a d factor. The correct result for this problem is dr, that's the cost of learning the subspace, plus r to the p. Given the subspace, you need r to the p samples to learn polynomials in r dimensions. That's kind of just the rate. And we're off by a factor. Okay, so we've been working on this with Maddie, of course, and Alex for a while. Actually, the second term, this dr to the p to r to the p is easy to improve. You just do some standard data splitting. So in the transfer learning setting, it's for free because in transfer learning, you just have a new batch of data. For the, so we just need to do some sample splitting. And then for smooth ReLU, we're in fact able to improve the first term to a d times r. Okay, and then there's some extra generality which I didn't talk about. Is this g, it doesn't need to be a polynomial as long as it's in the random feature reproducing kernel Hilbert space, everything is still fine because you're just mimicking kernel method at this point. Let me check my time. As usual, I'm very fast. Okay, so there's two future directions that I'm personally very interested in. One that I like the most is to look at the case where your features are now nonlinear. Okay, so so I have a function now that looks like g composed with a bunch of h's. The h's are nonlinear, the g is nonlinear, and I have r of these h's. So essentially, it's a function that only varies on r directions, but the directions are nonlinear, right? It's like only a submanifold matters for the y. Like the data can be anything, but only a manifold mattered. So you can consider a special case where these h1 to hrs are polynomial, g itself is polynomial. The current one is exactly when the h is linear. So the goal would be to learn this. Why is this an interesting model? One motivation is that it also allows you to remove the assumption that x's are Gaussian. For example, if you believe in GANs, let's say x came from a two-layer network, like A, nonlinearity of VZ, then if you can learn things of G of UX, it's exactly of this form. So a non-Gaussian data passed through a two-layer net is exactly equivalent to this kind of two hidden layer net, or three-layer network, essentially. Three-layer net with two hidden layers. So if you can do something like this, you can learn data also that's non-Gaussian. Also just nonlinear features seems to be somewhat more realistic. Okay, since I have some time left, I'll quickly, were there any questions? Maybe I should take questions now for this half. I think that's a better idea. And if there's lots of questions, I don't even need to talk.
Any questions for Jason?
Yeah,
Hi, Jason. Very nice work. I wanted to ask, how likely do you think that these techniques might apply if you just want to analyze plain gradient descent, like without the algorithm modifications you talked about, or like you probably need something totally different?
I think it's not totally different. I think if R is 1, you can do standard gradient descent. There are some issues when R is big. And kind of one major issue is that, so actually this animation was with standard gradient descent. And also it's R equal 1. So kind of this is very technical, but the issue with, when R is 1, the H is a rank 1. So if you just do gradient descent, it's like power method on H, and you just get the direction, and that's fine. But imagine that H is rank 2 now, and there's two eigenvalues of different size. One of them is 1, the other is half. if I do power iteration, I only convert to the top one, and I completely lose the second one. And that's disastrous. And that's the case I think I don't know how to handle.
Let me see.
Yeah.
Okay, thanks.
Yeah.
Hello. So you mentioned that you used network in mean field parameterization, right?
Yeah, everything here is mean field parameterized. Actually, the way I wrote the algorithm is actually any parameterization, but you should really think of it morally as mu p or mean field. Because I added this weight decay step that actually makes it work for any parameterization, but if you don't have the weight decay, it's for mean field. Yeah.
So in this respect, it's interesting. So in mean field parameterization, we kind of naturally have this feature learning ability, even when a width is infinitely big. But if you take, for example, the NTK parameterization, we would also have feature learning ability for finite network, but it would be like of a different nature because of finite width. So did you check like how your results change if you consider either this mean field, wide mean field network or like less wide NTK network?
Okay, so I think you started with saying, okay, first I have some issues with your claim. So when they say mean field learns features, it means the features move. It does not mean they proved it learned anything good, to be clear, right? Just because I move my features doesn't mean you've got good generalization error or sample complexity. So to be clear, there's no result in the literature that says, if I do gradient descent on mean field parameterization, I will learn good features. No such thing. So I think basically, and also there's no result I know of using NTK parameterization, but you force the width kind of to be small, and you escape it, and you learn good things, at least in any generality. There's also no results, I think, of that type. So I guess, yeah, so I don't really understand your question, taking into account my remarks.
Okay, maybe, okay, thank you.
Yeah.
Hi, thank you for the interesting talk. So just to add to the previous question, so for me, the way I understand this parameterization is that the only difference is that they give you different infinite width limits, right? But for finite width networks, isn't it the same, basically? Because you train maybe with different learning rates, so you get the same kind of representation.
Okay, so there's several confusing things here. Okay, so if you are willing to use per layer learning rates, you can always go between parameterizations. Parameterizations are sort of like, I have enough parameters to mimic any parameterization if you allow me per layer learning rates. So they're equivalent in the sense that if you tune per layer learning rates, yes, you can go from mean field to NTK. Does that answer your question?
Yeah, yeah.
Okay.
So I'll ask one question. Since it's ongoing work, maybe it's too early to say, but I'm curious about the direction you mentioned extending to nonlinear inputs. If you can talk a little bit about what making that kind of an adaptation might entail, in the sense of, do you need to use maybe a different algorithm, like for the sort of linear representation learning? You are taking one step.
The architecture I have in mind is different. Because you can kind of see this is going to be very hard to learn with a two-layer net, right? Because the first hidden layer cannot really, before the nonlinearity, it cannot express this. But then if after the nonlinearity, so you kind of, the algorithm I have in mind is a three-layer net with two hidden layers. And the feature learning is happening on the first hidden layer. And then you do a small number of gradient updates on the first hidden layer, and you hope those can learn the H's, and then after you get the H's, then you just fit a kernel method over the H's. Like, so the output of like, if I have, let me see if I have the notation here. If I have a learner that's 2 hidden layers, like the output of this part would be roughly the H's. And then to get the G part, I just add another A transpose ReLU of U, ReLU of VZ. That's kind of what I would imagine this looks like. We don't actually have any, the only case I know how to do it now is when, I think, let's see, the H's are like homogeneous polynomials, I think. Yeah, when the H's are homogeneous and the G can be general. Yeah, I think that case I think I know.
Thank you. And is there any relationship to the type of analysis you're describing in like the backward feature correction that we saw?
That paper is too complicated for me to understand. I don't know of anyone that's read it and said they understood it. Yeah.
Thanks. Any other questions? If not, we still have a lot of time, so if you'd like to
I still have a lot of time? All right.
discuss the rest.
Okay, I'll quickly talk about self-supervised learning. So kind of the setting of self-supervised learning, this is now work with Chile, who spoke a few days ago, is you have pairs of data, x1 and x2, and you want to learn a representation psi that only looks at x1 and x2, and that can linearly predict psi. There's two family of algorithms I want to talk about today. The first are based on masking or reconstruction, sort of you corrupt part of the input and then you try to like fill it back in. The second one is similarity methods or SimClare. SimClare, SimSciAm, think about that class of algorithm, where you tell it x1 and x2 are similar, usually they're augmentations of the same image. And I was kind of very interested that you have these two seemingly different family of algorithms and if there was some intrinsic connections. So this part of the talk is completely statistical. There's no algorithm whatsoever. Okay, so this is like a context encoder or mass autoencoder. Pikachu, his eye got deleted, and the goal is to reconstruct Pikachu's eye from the rest of Pikachu. So the architecture looks something like y is going to be a linear function. You learn psi. Psi is the reconstruction function. It takes psi of x1 will be roughly x2. And then you want to add on a head on top of the reconstruction to predict y. So that's the algorithm I'll look at. And that's essentially a context encoder. And MAEs are kind of similar-ish. Okay, so formally this is the algorithm. I minimize over my networks to get the psi. And then I train a head, W, to predict the y. And this works very well in practice. The goal is now, why does this psi get low error? This psi turns out to usually be very low dimensional, but yet y is in the span of the size. So it can linearly separate or linearly reconstruct. The other class of algorithms I'll look at, I wrote down SimSciAm here. I'm going to call it just canonical correlation analysis. It's essentially, to me, it's a nonlinear form of CCA, is SimSciAm. So what is CCA, or SimSciAm? Is you learn two functions, two eigenfunctions, or singular vector functions, psi and eta. You demand they're orthogonal. Let's just look at the case where they output a single scalar. It's a lot simpler. You try to maximize the nonlinear correlation between x1 and x2. So you're essentially asking, there's also a more intuitive reconstruction form, is basically given functions that are normalized have scale 1, psi and eta, how well can I predict psi of x1 from eta of x2? This is exactly CCA. CCA in traditional statistics is a linear form of this. The nonlinear generalization was done by like Brayman and Friedman. They had an interesting name called alternating conditional expectation. And it's a thing in statistics. Okay. So a very simple observation is that these methods are very similar and in a very precise sense. This masking objective in autoencoders or context encoder the optimum is going to be given by the conditional mean, right? The minimizer of square error is always a conditional mean. So if I want the optimal predictor of eta, it's going to be given like this. So if I had discrete random variables, when x2 can only take on a finite number of values, the mask objective, actually the minimizer, is going to be just a conditional expectation operator, or function, if you like. So just think about the discrete case, the conditional expectation operator applied to a Dirac delta function, everything's discrete, so it's just the conditional probability. And it turns out that the minimizer of that CCA function, you can show that it turns out to just be, you take this conditional mean expectation operator, it's an operator, a matrix, when things are finite, and you take the SVD and keep the top k. And that's exactly going to give you back the minimizer of the sim-SciM thing. So in other words, this masking objective plus a rank k PCA is exactly equivalent to the CCA for the discrete case. It's easy. So kind of using this observation, I already had a paper on analyzing these masking methods, and all I did in the slides is take all the theorems and convert them to now apply to sim-SciM. So kind of the regime we're thinking about usually for the masking methods is kind of the joint distribution between x1 and x2 is a nearly low rank operator. That essentially is equivalent to conditional independence. But x2 cannot perfectly predict y. So sort of mixture models, topic models are all of this form. The other case, when I look at sim-SciM, I'll be looking at when x2 can almost perfectly predict the label, but they're not independent at all. Sort of think of like, if I'm an image and I add some augmentation, the augmented image, although distorted, is still a very good predictor of the label. That's kind of like the second setting. And I'm going to have a measure of how close to low rank it is. Essentially, it's just the left minus the right. And that's how like not conditionally independent it is. Small is good, bad, high is bad. And then the correlation of x2 with y. That's the other thing though. So this slide is kind of confusing, but I couldn't figure out a way to present this well. So you have two algorithms and two bounds, so that gives you 4 theorems. So the representation error of either algorithm, anyway, is less than either of these two bounds. So there's 2 theorems, I take the min of them. The first, and the only thing different for the 2 algorithms is how you define these. One is the measure of conditional expectation, and the definition of correlation. So the only difference is that everywhere you see an eta, it's constrained to be linear in these masking methods. So sort of in the mask in autoencoders, you depend on the linear correlation of x2 and y, but in the contrastive methods, you depend on the nonlinear correlation. Like you can apply arbitrary functions. So rho is only better for the sim-SciM, but the other side gets worse. When you measure conditional independence, you want to fix eta to be linear, and it gets worse in the sim-SciM. So there's some trade-off here. And these trade-offs I wrote here below. So kind of, it's just a perspective to tell you that these, you can kind of look at these in a kind of essentially a unified way, that similarity and reconstruction are not too different. And of course, so let me just quickly conclude. For me, the major issue with this kind of statistical analysis only is it tells me nothing about why our algorithms or how our algorithms, the mechanism in which we learn good representations in mass autoencoders or contrastive learning. At the end of the day, I would still like an end-to-end analysis showing that SGD or on some architectures can do this. And that's kind of unclear. And that's all I really have.